Welcome, everyone. Thank you for joining the eighth Feature Store for Machine Learning Global Meetup. We're very happy to have you here. And today we have really great, amazing speakers to talk to you from the Kaskada and the Logical Clocks team. So welcome again. And before we get started, we just want to remind you that the meetup is being recorded, and we send the video to everyone. Will be available in our YouTube channel very shortly after. So thank you for joining us, and I'll pass it now along to Jim.
Hi, thanks Natalia, and welcome to the 8th edition of our meetup, the Feature Stores for ML meetup. Today we have two great speakers. As Natalia said, we've Michael RonDB, he's the head of data at Logical Clocks, talking about RonDB, which is a LATS database. He'll tell you what LATS means, but it's nice. It's a LATS database that powers the feature store in Hopsworks. And then we've Ryan Michael, who's from Kaskada. He's engineering lead at Kaskada. He's going to talk about overcoming data infrastructure limitations with a new paradigm for ML, which sounds really exciting. This is who we are. One point of note is, apart from the fact we have a newsletter and the publication page, there's an event coming up shortly within, I think, 1 month. It's the Feature Store Summit, and we have 25 speakers from really great organizations: AWS, Databricks, Microsoft, Spotify, Uber, Logical Clocks, and Kaskada there, and Berkeley, Stanford, and other places. So it's going to be a great event. It's happening over 2 days. It's a single track event, and it is free. So don't just join, but tell your friends and colleagues that this is an event that you should not miss. With that, I'd like to hand over to Michael, who's going to talk. And Michael had some screen sharing issues, so I'm just going to actually share the slides. I'm just trying to find where they are. Okay, 1 second. This is where we go. Okay. So I'm going to mute myself, Michael, and then it's over to you. You can just indicate to me when you want to change.
Yep. Yeah. So thank you very much. And so I'm Michael RonDB. I'm head of data at Logical Clocks. Before that, I spent 30 years at Ericsson, MySQL, Sun, and Oracle. So I have a long background in the database business. So I'm going to talk today about RonDB, how it can be used as a feature store, and why it's working very well as a feature store. So I hope my voice will carry the day, but we'll never know. So this is just the addresses of where Logical Clocks is. So I guess we can go to the next one. So what I'm going to talk about is first, where does RonDB originate from? So the second topic is, where do we actually use RonDB in the Hopsworks Feature Store? And as Jim mentioned, I'm going to talk about LATS and how that correlates to feature stores. And finally, we're going to look at some evaluations of DBMSs for feature stores that Spotify did, and also some comparisons using public documents towards TIDB, Aerospike, and Redis. So let's go with the first picture, which actually shows a bit about LATS. So LATS stands for low latency, high availability, high throughput, and scalable storage. So obviously, when you have a feature store, there is both the offline feature store and the online feature store. But we're talking here about RonDB mainly as an online feature store. I'm going to talk about RonDB's role in the offline feature store as well. But the main reason for the LATS is the online feature store. And in the online feature store, you can often have online applications where people are actually waiting for you, for the database, for the feature store to make a decision about something. For example, if you're performing fraud, if your financial transaction is valid or not, could be, for example, Spotify uses this to do personalized search. So it could be that you are actually searching for something to listen to, and you're not going to be wanting to wait more than at tops a few hundred milliseconds. And that means that the database has to perform its actions in just a few milliseconds. So low latency is obviously very important. High throughput, well, yeah, when you do the analysis, the machine learning analysis, it could be not just one row that you need from the database, it could be hundreds and thousands of rows that might be required. And all of those has to be served in a few milliseconds. High availability, well, if you're doing something like a financial transaction, you don't want the system to be down when you're trying to access it. So obviously high availability is also very important. And some customers, they want to have feature stores where they store many terabytes of data. So obviously scalable storage is also important. And so we try to put RonDB really in the center of all these. So that's why all these 4 qualities is qualities that a feature store could potentially require. Not every company will need all 4, but all 4 will be required by most companies. Okay, so where does RonDB originate from? It's based on a product called NDB cluster, MySQL NDB cluster to be precise. And I'm going to present 3 different areas where NDB is used heavily. So it's telecom applications, where NDB cluster is used as a universal database for about 5 billion subscribers, meaning that I'm pretty sure that 90% of you here today use NDB whenever you make a phone call. NDB cluster is also used in gaming servers, like, for example, when you play World of Warcraft and other Blizzard games, and a lot of other gaming companies as well. NDB cluster is also used in real-time financial applications, and the use case there is actually very close to a feature store. So I'm going to discuss that a little bit more. Okay, moving on. So the requirements on NDB cluster, and therefore the requirements that RonDB had to live up to, is handling 5 billion subscribers that do transactions against the database, and have to have. So when the telecom operators test the NDB, they have to show that the latency is below 10 milliseconds in 99.9% of the cases. And this is when they are at 90% load. So it's not when you shoot one transaction, it's when the system is almost overloaded and you still have to do complex transactions within 10 milliseconds. Downtime, it has to be less than 30 seconds per year. We actually, after about 5 years of operation, the downtime was about 0.2 seconds per year. But then they had a major event, and then so 30 seconds is what is the sort of average over about 15 years of operation. Okay, moving on. So gaming. So in gaming, you have many millions of concurrent gamers that want, for example, to log in. They want to have state of the game. And in this case, the clusters are a bit larger. So it's not just many small clusters. It's a few very large clusters, at least 16 big servers in each cluster. That is sort of, so it's a pretty big database that they have. The downtime here is not as high as on a telco server, but still people don't want the games to all of a sudden that you can't log in and play your game. So at most 5 minutes per year downtime is acceptable. And many of those applications also use complex SQL queries. So it's fairly complex queries, not just single queries, which actually is the same sometimes used in a feature store when you want to combine multiple feature groups, then that could also lead to complex queries. Okay, moving on. And then, as I mentioned, the financial applications, like, for example, a stock exchange. A stock exchange has millions of writes per second. So, for example, if you have NASDAQ, you will have millions of writes per second based on what's going on at the exchange. At the same time, you have a very high load of readers, which is very similar to how a feature store is used. You have the features coming in on the back from some background database, backend database, or a data warehouse, or wherever it comes from. And those writes have to go in, and at the same time, we have to serve quite a few reads on the front end. And in this case, in the financial side, we have to have latency all the way down to 100 microseconds. But that would be using special hardware. And the requirement here is basically no downtime at all while the exchange is open. But when the exchange is closed, well, then of course downtime is acceptable. Okay, moving on. So here is where RonDB is used in the features in the Hopsworks Feature Store. So as you can see, it's used by the online feature store, but it is also used by the offline feature store for the metadata of the offline feature store, and actually also for the files, for the metadata of the files. This picture shows how we get the data from the data warehouses and so forth. So we're using Spark and Kafka, and then we have a scalable stateless online ingestion service where the data is actually loaded into RonDB. And then we have the feature store API that goes and fetch the data from RonDB for the online transaction serving. Okay, so next picture. So here we see the 4 different parts where RonDB is used in the feature store. So it's used by the online feature store to store the feature groups and the features. It's also used for the file system, the distributed file system. So RonDB is a very critical part of the file system where all the metadata of the file system is stored in RonDB. And this file system is what the offline feature store is built on, something called Hoodie. And the Hoodie is on top of HopsFS. And then we have the Hive Meta Store, where the metadata for the Hoodie. So there's actually a lot of things. So RonDB is, in a sense, is the key cornerstone of our data management in Hopsworks. So it's a very, very critical part of our product. Okay, moving on. So we talked about LATs before. So as I mentioned, it's low latency, high availability, high throughput, scalable storage. So I'm going to talk now a little bit about why RonDB can deliver those critical qualities. Okay. So latency first. So one thing we gain latency is by using in-memory rows. The second thing is that we have a real-time scheduler. I mean, in an operating system, a time-sharing operating system, you cannot expect that you get more than, you will maybe have, if you have latencies of hundreds of microseconds between each task, it will be very difficult to meet the requirements on latency. So in most key value stores today, we are actually using a sort of real-time scheduler. So NDB had that designed in already from the very get-go. So this means that the scheduler, we have multiple threads in each thread. Each task gets about 1 to 10 microseconds per task. So that means we have an extremely quick switching between tasks. So you can have thousands of requests going on in parallel in just a millisecond. And in order to get to the data very quickly, we are using a distributed hash. So those are the three elements where we get the latency from. Actually, nowadays, disk data can, to some extent, also serve to sort of within latency boundaries. That was not the case 20 years ago, but today it's at least to some extent the case. Okay, next slide. RonDB high availability, I could probably talk about that for hours, but the most important thing is that whenever there's a failure, we will automatically rejoin the failed nodes. So there is no downtime due to the failure, and there is no downtime when the failed node is rejoining. And the rejoining will automatically synchronize itself with the live nodes. There is a lot of online management. You can add indexes, you can add columns, you can add nodes even to the cluster while it's up and running. We do support single node failures for small clusters. If you have a large cluster, for example, with 4 nodes, you can even have multiple node failures at the same time. You can have a whole rack going down, and still the RonDB will just continue like clockwork if you set it up to handle those failures. We have an immediate failover at node failure, so it could basically, if the failure, as soon as the failure is detected, we have reconfigured the cluster within less than a millisecond. So another important thing is that we only require 2 replicas for data durability. There are many systems today where they use quorum replication, and that requires at least 3 replicas for durability. So if you have 2 failures out of 3, you're gone. In RonDB, you can have 3 replicas, and if 1 fails, that's okay. And then you're down to 2 replicas, and then another one fails, and that's okay. Now you're all down to 1 replica. And then the replicas gets back again. Data consistency is also something we do. We can support transactions. We can support even transactions on many different tables at the same time in the same transaction. So that's not always the case in key value stores. Okay, move on. Throughput also comes from in-memory rows through real-time scheduler and from the primary key using distributed hash. But it also comes from some serious engineering on the networking side. So we have multiple levels of piggybacking on the TCP/IP messages. We have, one of the important things in my PhD thesis was to present CPU cache optimized index structures. So those means that we more or less minimize the number of CPU cache misses in the process of doing a key value lookup. We're doing thread pipelining, so that gets us very good throughput. If you want to get details about that, I have some blogs that has been written on that topic in the last couple of months. And we support up to hundreds of CPUs per node, so quite extensive throughput we can support. We actually did a benchmark already 8 years ago where we showed how to do 200 million reads per second in one NDB cluster. So I'm sure that if we did the same benchmark today, we would probably be doing billions of reads per second and billions of updates per second. So it's almost limitless, the capabilities on the throughput side in RonDB. Okay, moving on. And scalable storage. So in-memory databases tend to have problems with checkpointing, but we have solved that problem. So we can actually store up to 16 terabytes of in-memory data per node. And we can have 144 data nodes. So you can just multiply that and come to a number of petabytes of in-memory data that you could have in your cluster. On top of that, we also support disk data on disk. So you could have up to, for example, 100 terabytes of disk data on each node as well. And with 144 data nodes, well, I get to quite a few petabytes there. And we have showed that we can support write rates of many, many gigabytes per second. And we've shown efficiency of those writes that are much more efficient than other databases. Okay, next one. So there was a benchmark by Spotify. They wanted to look at personalized search using pre-engineered features for online search. And they wanted to be able to do millions of concurrent lookups per second and to see what the database or key value store that could scale to this. And it's the throughput and the latency that they were benchmarking. Availability they looked at by sort of doing a theoretical evaluation. Okay, next one. And so they found that Aerospike and RonDB were the ones that they wanted to particularly look at when they looked at the throughput, latency, and availability. They decided that Redis, Cassandra, and Bigtable were not considered for latency, availability, or throughput reasons. Yep, go ahead. And here you can see the numbers. So you can see that the numbers on RonDB is quite significantly higher than the Aerospike numbers. And in this case, they're doing more than 2 million lookups per second in this benchmark. Okay, and each row is a couple of kilobytes. So it's a fair amount of data that's traversing the network. And similarly here, we see the latency being better for RonDB. So here, lower is better. And primary transaction goes on in less than 30 milliseconds. Okay, yep, move on. So about 35% higher throughput, 30% better latency. And there will be some, if you want to study this in more detail, there will be a slide at the end which gives you links to all those presentations. Okay, next one. So we also did a comparison based on some public benchmarks of both RonDB and TIDB, where it showed that RonDB had 3 times higher throughput, 5 times better latency, and at 62% of the cost. And we actually had higher availability with 2 replicas compared to 3 replicas for TIDB, due to the fact that RonDB uses an arbitrator, so we can handle 2 replicas. We don't need 3 replicas to be highly available. Okay. And finally, we did some comparisons with open source Redis. Commercial Redis is not, you're not allowed to benchmark that due to some DeWitt clause in their license. So we set up a benchmark where we had 2 replicas, and Redis and RonDB had the very same setup. And the next slide shows how the numbers, we had a bit more than 1 million reads per second in RonDB and 750,000 in Redis. Okay, next one. And finally, we have this product comparison where we show low latency, high availability, high throughput, scalable storage first, but we also looked at data durability, data consistency, single failure support, multiple failure support, and SQL support, and showed sort of for the different databases what they support. So we didn't look at cost and things like that, because that's obviously not so easy to look at from. So, questions?
We have something in the chat here. Let's see if there's any questions. I don't know. So the benchmark with Spotify, Michael, it's that's this link here. Okay.
Yep.
And you know, when people talk about managed services, how do you see the managed services compared to, let's say, Aerospike and RonDB versus Dynamo and you know, Bigtable and so on?
Well, I mean, we're working very hard on making RonDB a managed service. So it's already now available as a managed service. And this is the main thing that we spend our days on, making it more and more manageable. Managing a database can be a bit tricky if you don't get the right management. And I think we're getting very much ahead of competitors there. It's also a lot of things in RonDB where management has been automated. In the past, there was a lot of things that was manual, where you had to configure things correctly, but nowadays it's almost automatic to configure. It's not just almost, it is automatic.
Thanks very much, Michael. And I think we'll pass over to the second speaker at the end of the time. So it's Ryan Michael. And Ryan, do you want to share your screen? Are we on here? Let's
absolutely. Okay, let's see. Let me share my screen here. Can everybody hear me and see my screen now, hopefully? Okay. Okay, so I am here from Kaskada to talk a little bit about machine learning. So the tools that we use to build machine learning models were designed to solve the wrong problem. And as a result, these models can take months or even years to put in production. So I'm talking about a particular class of machine learning models here, specifically models that are temporal, that either make predictions about the future or use features that change over time. So just to kind of ground this conversation, let's look at an example. So imagine that we have a video site and we have some users, and when they come to our site, we want to predict if they're going to watch an episode of Friends so we can make recommendations for them. And so just to kind of lay out some simple features that we might want to use as input to our model, we might want to ask how many times has a given user watched comedies. So maybe the genre is predictive, or maybe the age of the user is predictive. So how many times have users the same age as a given user watched Friends? And so these seem like fairly simple questions that we might ask as the input to our kind of trivial example model. But we need to talk about kind of how the model is produced, because there's two different contexts that we want to talk about here that are pretty different. The first is how we build the model, how we train it. And then the second is how we use it in production. So when we're training a model, we generally need to be building examples, large numbers of examples to train the model from, taken at different points in time. We want to be able to sample the behavior the model's predicting. We're interested in looking at large historical volumes of data so that we can capture as much information as possible. And we're generally optimizing for throughput, again, because of this large amount of data. But once we've finished training this model and take it into production, we have a different set of criteria that we're optimizing for. We're generally making a prediction based on all the information we have available to us at prediction time right now. And oftentimes the most recent data is the most important. And so these systems generally optimize for latency or freshness so that we can capture that recent information. And so if we focus in on the training case here, it turns out that our seemingly simple feature value or feature definitions rather get a little bit more complex, because we really want to ask a slightly different question. We want to ask the question of how many times had a given user watched comedies at the time that they began watching videos. In other words, we need to be able to limit our analysis to the point in time when this event occurred. But we're not done. It gets worse. Because again, we're building a training data set. So we actually need to build examples at every time a session begins. We're talking about a large number of different points in time that we need to travel to and produce training values. But we're still not done. Because as we discussed, we want to be able to make a prediction when a user begins watching videos, but we don't know the answer, the target value, until the end of their session. And so we're actually, to produce a single training example, we need to combine input features computed at one point in time and target values computed at a separate point in time. So what seemed at first like fairly simple feature values get a little bit more complex when we want to build a training data set. In production, we're back to the fairly familiar situation. We have a bunch of data. We want to answer a simple question. And this is the type of problem that most tools are designed to solve. This is the problem that I started saying is the wrong problem to solve. So let's take a look at how this is generally handled in most large distributed systems. In general, these aggregations operate by breaking them into associative and commutative pieces. We can distribute the data set across a large number of nodes, do partial aggregations on each node, and then combine them up. So for example, if we wanted to compute a sum, we might have this series of 5 numbers, break it in half, sum up 5, 4, and 2 in one place, sum up 1 and 8 in another place, and then we can bring the partial aggregates together to produce 20 in the end. And this works very well in these cases. We basically take our data set, break it up, merge them, and we're all good to go as long as our operations are associative and commutative. This is where we get to the problem. Time is not commutative. More specifically, operations that depend on temporal ordering are not commutative. We can't take this timeline and build all of these windows that we want in a commutative way. Our partitions cross all of those. And so effectively, each one of these windows, each one of these points in time that we want to travel to represent a separate aggregation. So the way that Kaskada has approached this problem is to start from a different starting point, to take a different paradigm, and to work from the perspective of chronological processing. Seems fairly simple, but basically what we do is that we process the data in the order that it occurs. Again, our goal here is to produce different training examples at different points in time. We want to be able to walk through time and produce an example of the user's behavior at arbitrary points in time. And so the fundamental operation that we use to describe what we're doing here as we produce these examples is what we call the stateful aggregation. So this is as opposed to commutative associative. What we're doing here is we have a function of some sort. It has a state and it processes a value, and the result is a new state. So for example, if we want to take sum, we can process the same sequence of events, and you'll see that rather than producing a single answer, 20, we produce a stream of values. This describes the result of this particular operation at every point in time. We're walking through our values and producing a new stream. So our fundamental data model is effectively a value paired with a time. And we process all these values in the order that they occur, in ascending time order. This means that we are consuming a stream of events that are associated with time, and we're producing a stream of values that are associated with time. Visualized differently, we could look at this as sort of a step graph, where each point in time describes the result of a computation. And this is our foundation. This is where we're going to start. We have this idea of point in time examples that we're going to process as a stream and produce values. As we process these, we're going to be able to produce examples or outputs with a single pass over the data. In other words, we can process the data once and produce multiple training examples as we go. And another interesting thing that we can do here is that we can use a single aggregator or accumulator as we move through time to produce multiple values. If you recall, we had a single function that we were threading across those 5 examples to produce 5 outputs, but there's only one value that was being threaded through each one. And so this is a starting point, but it's not sufficient. So there's kind of 2 big areas I want to talk about as shortcomings in the naive version of this. The first is that it seems to imply serialized execution. In other words, that we need to process every event one at a time in chronological order. Secondly, it seems to imply that there's only one way of ordering these values in time. And so I want to talk about both of these in turn, and we'll start with this serialized execution. So what we want to be able to do is distribute the computation so that we can do it in more than one place and reduce the time it takes to produce training examples. Traditionally, again, this happens through partitioning. And so we're going to look at a way that we accomplish the same thing effectively. And we do this by introducing the concept of an entity. So an entity is something like a user or a show, and it's just an identifier that we can scope our computation to. We talked about our data model as having a value and a time. That was actually partial. We also associate an entity with every value. Every value describes the time that it occurred, as well as the entity that it's related to. So to make this a little bit more concrete, let's bring this back to our example. We said that we wanted to calculate how many times a given user has watched comedies. So to partition this using entities, we would basically observe that we're talking about users here. We can partition all of our view events by the user doing the viewing. And then we can concurrently compute each partition's examples in chronological order. So we retain the chronological processing, but it is now scoped to a particular partition. And we can do this because all of our aggregations are scoped to entities. So for example, our feature that we wanted to compute, how many times has a user watched a particular genre, is shown here in our query language. So this says, count how many times a view by user's genre has been comedy. And we're showing here two different entities, Bob and Alice, users of our system. So there's two things to note here. The first is that on the horizontal axis, we have time. In other words, we are producing values that change over time. We are producing a temporal stream. And the other is to notice that these two entities are producing different values. In other words, we are scoping or grouping all of the values that we're aggregating by our entity. And so this gives us the ability to distribute our computation. But there's a catch, obviously. If we have a way of distributing all of our data into multiple places, we need to have a way of bringing it back together. It would be nice if we could break all of our computation down into small pieces, but that's generally not going to be the case. And so we introduced this idea of a point in time lookup, which is a really neat feature that we can do because we're processing data chronologically very easily. So let's talk through what we mean by this operation, or what this operation is for. Let's look at the second feature that we talked about. How many times have users the same age as a given user watched Friends? So we're going to walk through this in 3 steps. The first is we're going to determine how many times users of each age have watched Friends. In other words, we're going to build an aggregate related to ages. Second, every time there's a view event, we're going to determine how old the user who did the viewing was. And then we're going to use the result of the first operation and look up using the value of the second operation. In other words, we're going to say, well, when this user viewed a video, I know this fact about users of the same age. So we'll start at the beginning. How many times have users of the same age watched Friends? This is a similar expression, except we're using a table whose entities describe ages rather than users. And this is what that looks like. This is obviously trivial or a sample data. We're looking at 3 different ages, 31, 30, and 40. And we can see over time that people of each of these ages are watching Friends a certain number of times. Apparently our site doesn't have a whole lot of traffic. But notice that they're all monotonic increasing, et cetera, as you'd expect. So our second step here was to determine the age of each user when they watch a video. And we can do this fairly easily if we assume that every time someone watches a video that we capture the year that it happened in this case. And then we can just subtract when the user was born from when they watched a video. We assume that we have some information about each user. Now there's something interesting to notice here, which is that we're operating here between 2 different data sources. We have one data source describing views, another data source describing user info. And we're just subtracting the results of them. And that's because we have this concept of entity, which works as a join key, basically. Anytime we have 2 expressions with the same entity, we can just operate between them without having to specify join predicates. And so this is what we have here, is that we come back to our 2 entities, Alice and Bob, our 2 users rather, and we look at how old they were. So we see that Alice watched a video in 2019 when she was 30. And then later on in maybe the end of 2019, let's say, she watched another video after she had turned 31. Bob watched a video twice, both times he was 40. And so this is our kind of age value, which again, you can see has a time axis, as do all values. And so now we can tie these together. We can take the facts that we learned about ages and combine them with the facts that we learned around the age of each viewer. We can do this using what we call a lookup function. So we've just assigned these two expressions to name. So we've said watches by age equals the thing we looked at earlier, viewer age is the other. And now we're going to just look up the watches by age for a particular viewer's age. And here we have the result of that. So if we recall, Alice began, her first video was watched when she was 30. And so we can see that there were 305 views by 30-year-olds at that point in time. Later on, she watched another video when she had turned 31, and her number of watches has now changed to be 285. What's happened here is that we began by looking up information about 30-year-olds, and then we ended by looking up information about 31-year-olds. Bob has a slightly different case. Bob was 40 in both cases. Both of these values represent the behavior or information around 40-year-olds, but they're happening at different points in time. The first point in time, Bob was 40 and 40-year-olds had watched 516 episodes of Friends. The second time Bob watched a video, he was still 40, but 40-year-olds on average had watched, or in aggregate rather, had watched 525 episodes. And so what we're seeing here is two axes of how the lookup operation works in Kaskada. One is that it allows you to change the key that you're using to look up over time. And the other is that it allows the value that you're doing the lookup into to change over time. And each of these results will reflect the point in time at which you're doing the operation. So obviously, because we're partitioning by entity, and in this case, we partitioned by two separate entities, users and ages, we're going to have to shuffle between these operations. We call each pass of the data that we make a pass. A pass is basically an operation that reads some set of data, does some computation to it, and then potentially forwards results downstream. In this case, we have two passes, one reading information about users and one reading information about ages, and then communicating between them as the first pass learns which age is associated with each view event. And so these passes form a graph through time where they're passing data back and forth. So let's step back and summarize where we are so far. We started by looking at chronological processing as a different way of approaching feature computation that could help us build training data sets. We introduced this idea of an entity that allows us to distribute our computation by entity partitions. Within each of these partitions, we're going to process all of our data chronologically. And then we talked about how we can combine entities in different partitions using this lookup function that we provided. So there is one catch that might be worth mentioning briefly, which is that relative to a standard MapReduce or Spark operation, in some cases, we'll be shuffling a lot more data. We talked about how we're going to have to determine the age of every view and then use that age to look up how many times people of that age had seen Friends. That's potentially more data than we want to, we're potentially shifting a decent amount of data there because we're not putting that through a pre-aggregation step. But we have a number of optimizations that actually can help with this substantially. So let's circle back to the second thing we wanted to talk about, which is how we can deal with time. We've talked now about how we can make the computation performant and how we can do, or we can handle multiple data sources. So let's talk about what we call native time travel. And to motivate this, we're going to look at this example we touched on briefly, which is that in order to build a training example, we need to know some information computed at one point in time, namely the input to the model, which will be computed at the beginning of a viewing session, and some other information computed at another time, namely the target value, whether or not the user watched the show Friends during that particular viewing session. So to restate, when a user begins watching a session, we want to predict if they'll watch Friends. And so we can accomplish this by describing the features that we care about. We described two features. We went through how we might compute both of those. And then to limit this to particular values that we care about, we're going to want to filter these features down to the times that we care about. So we'll look at this in a tabular form. So here we basically built a set of features using the expressions we explored earlier, the number of times each age or people of that age have watched Friends and how many times that user has watched comedies. And then we're going to add the number of times they've watched Friends as well. And we'll just filter this using this when function down to a specific set of times when the session began. Notice the start time for Alice's first row is 8:15. And then we said the second thing we wanted to do was to build the target value. We want to know, will they watch Friends during that session? We can do this by counting how many times they'd watched Friends at the beginning of their viewing session, and then comparing that to how many times they've watched Friends at the end of that session. In this case, we'll use what we call a shift operation to capture the count at the beginning and move it to the end. We'll move it forward in time. And so in this case, you can see that we use this shift until operation to capture all of the features that we wanted to use to make predictions and move them to the end of the session, move them in time to the end of the viewing session. So you can see now we've gone from 8:15 for Alice's first row to 8:45. And now we've been able to label our target value. We know that Alice watched Friends on the first time that she watched, and Bob never watched Friends because he doesn't like Friends. And so this is the way in which we can take values computed at different points in time and bring them together in a time-safe way. We effectively take values, shift them forward to the end of the session. Now, there's a slight complexity here that I want to touch on briefly, which is that when we're shifting these values forward in time, we may shift them by different durations. And so the order may change. The values produced by this operation may have different times and a different order than the values consumed for this operation. And so in order to accommodate this, we introduce priority queues within each partition between these operations. The nice thing about processing this in order is that we don't actually need to put all of the values produced by a pass into that priority queue. We only allow values to be shifted forward in time. Shifting them backwards in time would represent learning about the future. And so for any given set of passes, if pass 2 is consuming the results of pass 1, as soon as it gets to a value that has been emitted by pass 1 and is older than the current time of pass 1, but newer than the current time of pass 2, it can consume that value. And so we are able to keep much smaller queues in place when doing this operation. And we're able to start work on downstream passes much more quickly than if we had to produce the results for an entire pass and then sort and then process the next stage in the operation. And so here's where we are with the time thing. We've talked about the way that we can describe temporal relationships natively as code. We've described filters and shift operations that allow you to time travel using your expressions and describe the relationships between different values computed at different times. And this allows you to compute training examples on demand. You don't need to go through and backfill new features to create historical snapshots, et cetera. You can simply describe how you want your values to come together and they will be computed in that way. And we talked briefly about this optimization where we can begin computation on downstream passes before the upstream passes completes, even though there's an ordering operation in between the two of them. And so this is kind of where we are so far. If we step back, we can now talk about how we can do this chronological processing of data. We talked about a way that we can efficiently parallelize the work that we're doing so that it can be distributed. We talked about how after we've partitioned this data, we can bring it back together in various ways using lookups. And then we looked at the ways that processing the data in order makes it easy to use kind of native time operations to describe the relationships between values at different points in time. And so the net effect of this is that you are able to write features in a much more concise and intuitive way, in a way that maps more natively to the way that you think about the experience of time and the way that you might want to describe the features that you are computing at different points in time. This is the sort of summary of what we've done so far. And once you've built one of these kind of set of feature definitions, it's much easier to iterate on that. We can change the definition of when we want to capture our features or when we want to describe the target value. All of these things can be changed with simple code changes with no need to go recompute large amounts of data. And most importantly, because taking things to production really just means evaluating the value right now. We can take our features directly to production with no changes. And so to bring this back, I began by saying that the tools that we traditionally have used to solve machine learning problems are solving the wrong problem. And the problem that they solve is the productionization problem. And what we're arguing here is that the training problem is actually the harder problem to solve. And that once you've solved that, going to production is much easier. We believe that ordered chronological processing provides a better foundation to build machine learning models. And so please, it's free to sign up. So if anybody's interested, I would love to hear people's comments and feedback. So thank you. I can stop sharing.
Thank you, Ryan.
Thank you, Ryan.
I have a question.
All right, Jim, go ahead.
Yeah. So when I hear ordered chronological processing, I really think stream processing. You know, I think this should be executed with stream processing engine, and you partition by user ID or entity ID. And what is the execution model for this platform? Is it stream processing? And the other one I think of it when I think of batch, I think of partition. You have a partition column, and then you bucketize within it. So you have your partition by, let's say, entity ID, and then you bucketize by timestamps. You're ordering within the partition by timestamp. So how would this fit into those two schemes?
Yeah, so I think obviously there's a lot of inspiration from stream processing in here, as you can imagine. I think that we expect that the production use case will look very streamy. I mean, people are going to be, we ingest data from Kafka. So like that is a very similar use case there, where we want to keep a production feature vector store up to date as we're processing data. And I think that is largely a streaming application. What we're doing a little bit differently is that we're applying the same sort of processing techniques to the historical data, right? Like building the training data set in the first place and optimizing the execution engine for handling large amounts of data, rather than just, I mean, stream systems, you expire that after a day or a week or whatever. And so you can go back and build features that are a week old if that's enough data for you. But oftentimes you need more look back, you need more historical backfill. And so there are ways of kind of taking these systems and using them in batch operations. But even most of the streaming systems like are trying to expose an interface based on this associative commutative kind of way of thinking, this sort of map reducey way of coming at this problem. And I think that what we've discovered is that starting from a different place allows you to describe things in a much more natural way that just kind of makes these things easier in both cases. Dabra, I don't know if you wanted to follow up on that. You look like you were.
Maybe I would have a slightly different, more concise answer, but I would. All right. I don't think we have any questions submitted in chat or Q&A. Maybe last call for questions. If any of the participants, attendees would like, any more context on either on these two talks. All right. We'll give it.
Thanks, everyone. There is something.
Okay.
How does this speed up the process you started with? Right.
All right.
Show me the money.
I don't know.
Yeah.
Show me the money. Is that?
Yeah. So I think sorry, can you hear me? Yeah. Okay. So the benefit there is that because you can work in a more native kind of environment, it's much easier to describe the operations that you need. And so iteration is much faster. You can explore new features. You can try different ways of combining them. And it's just a computation. It's kind of like a SQL query in a sense, except you have a more diverse set of operations that you can apply that are more finely tuned to the particular problems that we find data scientists are generally trying to solve. And so it's not necessarily that the computation is faster. Like we're not making an argument here that like we've made compute much faster. It's more about the kind of cognitive or the like mental models that we're providing more closely aligning to the problem space. And so you can work more intuitively and more naturally and get into that kind of like flow state of trying things out and seeing the results and like trying new things out.
All right. I think that concludes all the questions in the meetup for today. I'd like to thank everybody for attending. Obviously, this video will be posted online. Please do sign up for the mailing list and you will get access to this recording, I think, sooner. And please don't forget about the Feature Store Summit that is happening next month. It's in about 4 weeks, I think, October 13th, 14th. It's a free event with a great lineup of speakers. So don't forget to tell everybody about it and please sign up. I think it's gonna be a great event. And we will probably see you shortly thereafter, maybe it's a month after that, for another instance of a Feature Store meetup, hopefully with another great lineup of speakers, most likely from the industry. With that, I think we can end here. Obviously, as always, thanks to Jim, Natalia, Mikhail, and everybody for helping to make this one happen. And Ryan as well.
Have a great one.
All right. Thank you all.
Bye now. Bye.
Thank you.